40 is on parametric equations. So you might have dealt with parametric equations before, but we're going to do a little bit more in this section so that we can do even more next chapter, which is involving like polar coordinates. Have you guys ever seen like people draw like flowers and stuff on their graphing calculator and you've been like, wow, how do you do that? Or spirals? That's using polar coordinates. So it's always fun to graph. All right, so it says, suppose you were throwing a rock straight into the air with a velocity of 35 feet per second. So if you didn't have gravity, then the rock would continue to go up, up, up. It would never come down, 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 right? So after 1 second, it would go 35 feet. After 2 seconds, it would go 70 feet. Does this make sense? So we're just going to plug in. So 35, 70, 105, 140, 175. Okay? And it would never come back down. It would just continue to go up. But if gravity is figured in, then we know all things that go up must come down on Earth, right? So the gravity constant is negative 32 feet per second squared. So with a little bit of calculus, basically your height equation ends up being half of that 32 t squared. So here's what we would get, 35t minus 16t squared. Okay, so since I have to find several values, I'm finding 1, 2, 3, 4, and 5. I'm going to go ahead and put this into my calculator as y1. So I'm going to put in 35x minus 16x squared. And then I'm going to go to my table. Maybe I should do that on my little calculator so you guys can see. So I'm going to y equals, and I'm putting in 35x minus 16x squared. Okay, and then when I do a second table, mine already has the values in here. Yours might not be in here. You can always do second table set and make it so your independent is ask. And then you can put in whatever values you want. But I actually had them already. I should have just kept them. So like 1, 2, 3, 4, 5. Okay, so we have those numbers. So after 1 second, you would be at a height of 19 feet. But then after 2 seconds, you're at a height of 6 feet, which is kind of weird, right? So gravity has already pulled it back down. All right, and then at 3 seconds, you'd be at negative 39. Can that happen? No, you'd really be at a height of 0. Does that make sense? So you'd be on the ground, on the ground, on the ground. So it's going to take between 2 and 3 seconds to hit the ground. Okay, so you can fill in those numbers. Go ahead and fill in 19, 6, negative 39, negative 116, and negative 225. You gotta help me out. Negative 39, what did I say? Negative? And then negative what?
225.
So these are on the ground. Okay, so this is where the equation h of t is equal to negative 16t squared plus v sub o t plus h sub o comes from. Okay, I'm sure that you've seen this before. Okay, this is in like every single Algebra 2 textbook and so on. I forgot to raise my 2 there. But this is our height for anything, we call it projectile motion, anything that you're throwing up and it's coming back down, okay? So it's gonna make like this kind of shape here, like a parabola. All right, so it says, suppose we don't throw the rock perfectly vertically. We're not throwing it straight into the ground and then straight back down. So really it's not the parabola, it's really just straight up and down. Instead we throw outwards at an angle of inclination. Okay, so in order to do that, we're gonna have to start talking about vectors. Okay, so if you're throwing something at an angle of inclination of 30 degrees, you're still going to have like gravity pulling it down, okay? But your initial velocity, so if your initial velocity is 35 feet per second, it's in that like diagonal direction. Does that make sense? But we have 2 components to that. We have a vertical component, the one that's moving up and down, that's affected by gravity, and we also have a horizontal component. Okay, so we want to know like how far the rock is going to travel. Okay, so what we end up doing is we break it into 2 different things. Okay, and we'll often call these Vy and Vx. Okay, it's actually like V sub y of 0. V sub x of 0. It's the height, or the initial velocity, so at time 0. Does it make sense? Sometimes we write it, which is really fun to do a subscript of a subscript, like that, but I'll just do of 0. All right, and we can get these initial velocities using Sohcahtoa. We love Sohcahtoa. We've used Sohcahtoa in like every chapter this year. All right, so if you're doing this, and you wanted to find V sub y, that's going to be opposite our angle, and then we would use the hypotenuse of 35. Does that make sense? So if I wanted, let me write the equation first. So if I want this, I'm going to do sine of 30 is equal to opposite v sub y of 0 all over hypotenuse, like that. So do you guys see that the y component for the initial velocity ends up being 35 times sine of 30? Right? Does that kind of remind you of vectors a little bit? What do you think the x component's going to be? Yeah, exactly. Do you guys remember when we were trying to get vectors in component form, but we just had the angle, what we would do? So if we want the initial velocity v sub x of 0 and v sub y of 0, what we do is we end up just taking 35 cosine of 30 and 35 sine of 30. Run out of room. And you can find those numbers. So just make sure that you're in degree mode. So if you do 35 cosine of 30 and 35 sine of 30, you end up getting 30.311 and 17.5. Okay. So really what we're saying is that along the diagonal it's going 35 feet per second, but vertically it's going 30.311 feet per second, and horizontally it's going 17.5 feet per second. Do you guys understand that concept? Like, it's not going the same speed like horizontally, like out and up. It's kind of weird. All right, so it's related definitely to the component form that we've talked about before. Okay, so then your height, the height is affected by gravity, right? So your height equation ends up being y of t equals, it started at a height of 0, right? We were throwing it up from, well, I didn't really say we're starting at a height of 0. And we use this equation, right, our height equation. Oops, moved everything. Okay, so we're going to have negative 16 t squared plus our initial velocity times t plus our initial height. Okay, so it's going to be whatever that v sub o in the y direction was. So it was 17.5. And then plus 0. And then the horizontal distance, it's going out horizontally. There's nothing like pulling it backwards though, right? Like gravity, we don't have that negative 16 t squared for the horizontal. Do you guys understand? Like ideally it would keep going, but eventually everything's going to hit the ground. So imagine you're kicking like a field goal. Like if you didn't have gravity, wouldn't it just continue to go out horizontally forever? Yeah, it wouldn't go back down. That would be like, you'd be the best kicker ever.
Well, I mean, if you kick it hard enough, it can keep on going because it'll just get to a point where
Is that an equation below the table is supposed to be t squared? Or is it supposed to be t?
It's t squared, yeah,
Okay.
t squared. All right, and your x component is 30.311, so that's going to be, we're saying for every single second, right, it's going 30.311 feet. Okay. So it says, find when the ball hits the ground, how far has it traveled horizontally at this time? So if we want to find when it hits the ground, we want to find when the height equals 0. Right? So we're going to take this equation that we had, and we're going to set it equal to 0. So we're going to have 0 is equal to negative 16 t squared plus 17.5 t. Right, and we solve for t. So if we're solving for t, we're just going to pull out a common factor of t. So I'm going to have t times negative 16t plus 17.5. And we're going to solve. So when I set, like the first answer is t equals 0. That's when it's actually on the ground. It started on the ground. Does that make sense? And then the negative 16t plus 17.5, when you set it equal to 0. And solve. Do you guys get it? It's like 1.09375. That's the time it takes to hit the ground. So a little bit more than a second. If it's taking like 120 seconds for a ball to hit the ground, right? Maybe it's like a balloon. I don't know. Then you've done something wrong, right? It's usually going to be a pretty small thing for time. So the second part of the question is, well, how far has it traveled horizontally? So how do we think that we find that? If we want to know the horizontal distance. We don't use that vertical equation anymore, yeah?
Set it equal to 30.311.
Not set it equal, but we plug it into the 30.311 t, right? So we have the t, so we plug it in. So we're finding x of 1.09375. So we're plugging it in. So 30.311 times 1.0395, or 375. So keep that number in your calculator and just multiply by 30.311. And you could have stored your 30.311 number. That would have been a little bit better, but that's okay. So 33.153. Mm-hmm.
Where did you get the 30.311 from?
It is from when we did the sine and cosine. So the 30.311 was our 35 cosine of 30.
Okay.
It's the x component for the velocity.
I thought the 1.09375 was when it hits the ground again.
Yeah, so it's when it's hitting the ground. So we're saying when it hits the ground, how far has it traveled total horizontally? Does that make sense? So you're going up and you're coming back down, and we're saying that it takes this long to hit the ground, and then this distance ends up being something. So t is a time. X is what you want for the distance. Okay, so that's why we need to use parametric equations. We need to be able to talk about x components and y components, heights and distances. So when does it reach its maximum height? Okay, so if you're reaching its maximum height, that means that we're going to find the maximum of the height equation. Do you guys remember how to do that? Ah, yay. Yep, a formula from first semester and from Algebra 2, x equals negative b over 2a. But it's not x equals in this case. I guess it's t equals, right? So we're going to have negative 17.5 over 2 times negative 16. So I got 0.547 seconds. So that was in seconds above, too. All right, so if I wanted to know its maximum height, then I plug that into the y of t equation. Does this make sense? So we have our two different components. All right, Alessandro, I have a question about you. All right, Alessandro plays, did I spell it right? I don't think, did I spell that name right?
Yeah.
Okay. It always looks like an I on your homework. All right, Alessandro plays football for the first time with his friends, and he realized that he is a natural at field goals. He practices kicking the football 35 yards, which is 105 feet from the goal post, which has a crossbar that's 10 feet high. Okay, so you guys know this whole drawing, right? You got this? Got this figured out. If he kicks the ball with an initial velocity of 65 feet per second at a 46-degree angle, we want to know if he's going to be able to will he be able to make the field goal? Will he make what's a he? All right, so we want to know if after this distance, right, our horizontal distance of, how far away is he, did I say? 35 yards away, so 105 feet. We want to know how high it is after 105 feet. Okay, so we come up with all of these components. So our initial velocity, it has two components. So we need to break it into its x component and its y component. So when we do this, it was 65 feet per second at an angle of 46 degrees. So it's going to be 65 cosine of 46 and then 65 sine of 46. It's just finding the x and y components of a vector. That's all we're doing. The y of t is going to be negative 16t squared plus whatever this 65, I'll go ahead and write it in there, 65 sine of 46 is, times t.
46.
Yeah, 46 degrees. Oh, you found it? Okay. And then plus, he's kicking it from the ground, right? That would be awesome if he could throw it in the air and kick like 3 feet up, but it does not happen that way. So plus 0. All right. And then our x equation, x of t, what would that be? 65 cosine of 46 degrees times t, right? So for every second, it's gaining that much. Okay. So we want to know after 105 feet how high it is. So tell me how to do that. How do I find how many seconds it took to get to 105 feet out and along the x direction? Maybe I'll say x equals 105 feet. So how many seconds does it take to get there? Well, we just take our x of t equation, right, and we set it equal to 105. Do you guys understand that? You guys are very quiet today. It's just rainy and you just don't want to do math, huh? You can handle this, I promise. All right, so we're going to get that. So we're going to take the 105 and we're going to divide by, and I'm just going to go ahead and put it all in my calculator just like that. So 65 cosine of 46. So I get t equals 2.325. Okay, and I want to keep that as precise as possible, so I'm going to store. Yeah, Catherine?
Why don't we set the y of t equal to 10 and then see?
You could, it's just harder to solve. You'd have to do like quadratic formula and all kinds of stuff.
But you could do it.
You could do that, and that would be saying how long does it take to get to 10 feet, but then the tricky part of that is there's actually two places where it's at 10 feet. If it goes over 10 feet, does it make sense? On the way up and on the way down. So there would be two answers. So you'd kind of have to interpret. All right, so we want to find out how high the field goal is at 10 or at 2.325 seconds. Right, so what do we do now?
Plug it into the y equation.
Yeah, plug it into the y equation. So you're going to have y of 2.325, and I went ahead and just stored that number. So I'm going to be as precise as possible. So I'm going to write it as a. Do you guys all understand this notation when I write an a there? Do you guys remember doing that first semester? Like that. I said I stored it, and then I actually never stored it. So now I'm going to really mess up. All right. So store as alpha a. Okay, so then I'm going to do negative 16 answer squared, or a squared. Anybody got it?
22.208.
That is exactly right. Did he clear it? Yeah, he's a beast. He cleared it.
Oh,
But, you know, if you guys watch any bowl games like IU, if you go over the field goal and they can't tell, then they just say that it wasn't in. Did you guys see that bowl game? It was rough. It hurt my heart a little bit. So basically it went above, and if there was an invisible line, it was right there, but the ref couldn't tell, and so he said that it wasn't good, and then IU lost their bowl game. It was sad. All right. So yes, Alessandro is a beast, and he can kick it very, very far. He should maybe scoot back a little bit, shouldn't he? All right, now it's Tyler's turn. Tyler, did you play baseball?
Yes.
I knew your older brother did, but I was like trying to think of someone in the class that played baseball. Just like, All right, so Tyler hits a baseball. I thought you did. Straight towards a 14-foot fence that's 410 feet from home plate. The ball is hit when it's 2.75 feet from the ground. So baseball, you don't hit it off the ground, right? And it leaves the bat at an angle of 32 degrees. Find the initial velocity required to clear the fence. Okay, it's a little bit harder. All right, so yes, let's draw a picture. So it's from 2.75 feet. And he's hitting it, and it's at an angle of 32 degrees. And this initial velocity is, oh, that's what we're finding. So we'll call it V, or V sub O if you want. All right, and he's trying to hit it 410 feet from home plate, and he wants to clear a height of 14 feet. Okay, but obviously it's not just going straight up forever, it's going to come back down, right? So we have a little parabola situation going on. So if we write our components are our initial velocity, we're going to have our v, whatever that is, times cosine of 32, and our v times sine of 32. And our equations, right, we write our y of t and our x of t equations. Do you guys have this down yet? So it's going to be negative 16t squared plus whatever our initial velocity in the y component was, so v sine of 32 degrees t, plus what's its initial height this time?
2.7.
Yeah, 2.75. And your x of t also involves this v that we don't know, cosine of 32 times t. Maybe I should put parentheses around that. The t's and the pluses are always tricky. All right, so we want to know, like, at 410 feet, well, this one is kind of a tricky one. Okay, so 410 is going to be our x value, right? So we're going to go ahead and plug in 410 for x. So that. All right, and it's going to be momentarily messy. I'm going to put it down here where there's more room because I drew my picture way too big. So if I solve for t, I end up getting 410 divided by v cosine of 32, right? That's going to be the time that we plug into the y of t equation. And what's y of t going to be set equal to? We want it to clear the fence, so we want it to be 14. Does that make sense? Or 14.1. Like, we don't want it to just nail the end of the fence, but whatever. All right, so we're going to say 14, though. So we're going to have negative 16, and then we're going to plug in what t is. So like I said, it's going to be a little bit messy for a sec, and then we'll clean it up. So we're going to have 410 over v cosine of 32 squared plus, I know, oh, you're fine. Oh, you guys have done things like this before. All right, 410. Okay, so we get that. Okay, and then you can actually solve for v with this. So do you guys see what's going to happen? These v's are going to go away. You get it? All right, and then we're going to have something with a v squared. So let's go ahead and do some algebra to bring this over. Can you guys follow along with your calculator?
Wait, where did you get all those bottom equations?
I solved for t using this equation, right? T was equal to 410 divided by v times cosine of 32. And then I plugged it in.
All those equations on the top right then. You use them to find the bottom one, right?
Yeah, so I plugged into here. So I replaced all my t's with that. You could have also solved for v and replaced your v with that, and then solved for t, but it's going to be a little bit harder, I think. All right, so here we go. So follow along with your calculator. Everybody have their calculators out? So we're going to do 14. Let's subtract the 2.75 over. So we get 11.25. All right, let's find what all of this mess is. So we're going to do minus, parentheses, sine of 32 times 410 divided by cosine of 32. So right now I'm at negative 244.946 equals negative 16 times 410 v cosine of 32 squared. Okay? All right, so we have that. So now I'm going to take that number and I'm going to divide by negative 16. You got it? So 15.309 equals 410 divided by v cosine of 32. What do you think my next step is? Squared. Get rid of the square. Square root. All right, and then I'm going to multiply, I'm going to do some moving around. So I'm going to multiply 15.309 by v cosine of 32, and that's going to equal 410. So I'm going to take my 410.
Isn't that the square root of 15?
Yeah, the square root, thank you. So I'm going to take that 410, and I'm going to divide by that answer that you just had, the square root answer. And then I'm going to divide by cosine of 32. So what's his initial velocity required? Did you guys get 123.563 feet per second? Okay, that's about as hard as they get. So when you have to find the initial velocity, it basically is a system of equations. You have v and t that you're solving for. All right, moving on. So this part's easier. So we're going to use our calculator. So it says we can graph parametric equations by hand, which will actually be pretty useful for us in these types of situations. So we're going to talk about how to use your graphing calculator, what we can do to solve these types of problems, okay? So it says we can graph parametric equations by hand, and we can use our calculators too. So if you have a certain domain for your t-value, hit window and adjust the t-min and t-max. So I'll talk about that. So let's say I want to graph this parametric equation. Notice how we have x equals and we have y equals, right? Right now, when you try to go and hit graph, and you hit y equals, oops, it doesn't like me. Guess I gotta open this up again. It's not letting me click it. All right, when I hit y equals, it just says y equals, right? Parametric equations should always have x equals and y equals. Okay, so here's what we're gonna do. So get your calculator out. You definitely wanna know how to do this by using your calculator, right? Unless you want to on your test do all that by hand that we just did. It's up to you. All right, so as I do this, I'm gonna do mode, and I'm gonna go down instead of function, I'm gonna go over to PAR, parametric equation, hit enter. And I'm gonna go to y equals then. Do you see how we have x and y going together? That's what we want. Okay, so for this picture that's in your notes, let's go ahead and graph that. We have t squared minus 2. That's what x is equal to. And then y is equal to 3t. Okay? Notice when you're hitting the x button, it's actually putting in a t. Does that make sense? Do you guys all have that? 3t. So right here. So when you hit graph, it's going to give you a picture. Okay? It looks kind of like a square root function. All right, but notice how these pictures, and yours might look different than mine depending on what your like if you do Zoom 6, the standard. Yeah, now ours will all look the same if you do Zoom 6. All right, now for A, B, and C, it has portions of that, but it actually is going below the axis. Okay, it's using t values that are negative as well. Okay, so what we would do is we would go to window, and we'd have t min is -3, and t max is 1. I would say don't adjust your t-step. Leave it like 0.13, whatever it is. That's like telling how many points to graph, basically. If you make it really, really tiny, it takes forever to graph, so we'll just leave it like that. So when we hit graph, do you see how it's only giving you that portion? Does that make sense? But if I change it to -2 to 3, it's going to give me this portion. If I change it to -3 to 3, it's going to give me that portion. Okay, it's basically saying if you set up a t-table, like if I literally did a t-table for part A, for a parametric equation, a t-table looks like this. Okay? That's your domain, like this thing. Those are the numbers we're putting in. So it would say, like, pick numbers that are between -3 and 1. So those are the types of numbers you'd pick. You would plug into the x equation to find what x is. So if I plug in -3, I'd get 9 minus 2. I'd have 7, right? And then I'd plug in to the y equation to get what y is. I'd have -9. So that means you would have the point 7, -9, which is right there. Okay, does that make sense? So you would be able to plot all these different points doing a t-table. Okay, or you can just do it on your calculator like that. So let's revisit the last one. So let's go ahead and in our y equals, let's put in the x equation and the y equation. So the x equation is going to be Well, I guess we didn't find that we can't do this for this last one, can we? We can do it for the other because we still don't know v. Oh man, I thought we could. All right, so we could do it for the first one though. All right, so let's try some of these. So number 1a. So it says sketch the curve given by x is equal to t squared plus 4 and y equals t over 2, where t is between -2 and 2. So I already gave you this little table. Okay, so we're just going to plug in these numbers. So if I plug in -2 into the x equation, do you guys see how we get 8? Then we have 5, and we have 4, we have 5, and we have 8. Do you guys get those? All right, if I plug in -2 into the y equation, I get -1, -1/2, 0, 1/2, and 1. So if we were sketching it by hand, we would have the, like, you basically ignore the t's. You graph these points. So you'd have 8, -1. You'd have 5, -1/2. You would have 4, 0, 5, 1/2, and 8, 1. So do you guys kind of see what shape it's looking like? It's probably going to be a parabola. Do you guys see it? All right, but it's going to stop. I guess I shouldn't have drawn this all the way because it's going to stop at -2 to 2 because that's where its domain ends. So it's actually going to be only that portion of the parabola. All right, so if we put that into our calculator, like you could do t squared plus 4 and then t over 2. Are you guys all understanding how to graph this on the calculator? Everybody has their calculators out and they're trying it. And your window, though, would be from -2 to 2. So when you hit graph, it just draws that little portion. Does that make sense? All right, so what I'll be saying is I'll say things like eliminate the parameter to write the rectangular equation. Okay, so if you're eliminating the parameter, what you're going to do is you're going to take your x equals t squared plus 4, and you're going to take your y equals t over 2, and you're basically going to solve like the system of equations. Okay, so for the y equals equation, do you guys see how it's really easy to get t by itself? That's what we want to do. You always want to get t by itself. So t is equal to what? 2y. Do you guys see that? So then you go back to your other equation and you replace your t with 2y. Okay, so you're going to have x equals 2y squared plus 4. So I get x equals 4y squared plus 4. We've now eliminated the parameter. Okay?
Where'd you get the 2y?
I solved for t in this equation. So I noticed that t, if I multiply the 2 over, I have 2y. And then you replace it in the other. Do you guys think you can do that? All right, let me pause and you guys can go on break. Hang on. All right, so the next one says graph x equals sine of t and y equals sine of 2t using your graphing calculator. So if you use your graphing calculator and you want to see what this little shape is, when you go to your parametric equations and you put in sine of t and then sine of 2t into your calculator and hit graph. Well, we want our window to be from 0 to 2 pi, so let's change that. 0 to 2 pi. So t min, t max, you're changing. You guys all doing this on your calculator? All right, and then we hit graph. Okay, what do you get? Can you see it? It's like a little infinity sign. You can zoom in if you want. Like you can make your x min and x max smaller, like -5 to 5. T-step should just be like, don't mess with that ever. I usually have it like around 0.1, somewhere around there. That's basically saying like if you start at, we started at 0 for our t value, and it's going to include, if it was 0.1, it's going to include 0 in the t table, 0.1, 0.2, 0.3, 0.4. But like Lauren had her calculator, and for some reason it had like 7.5 for the t-step, so if it starts at 0, then the next thing it would put into the t-table would be 7.5, so it's not going to give you like a very like smooth curve. All right, so yeah. Cute. All right, so you will definitely, like, you have some homework problems. I think there's like 6 where you're just putting it into your calculator and you're identifying what the shape is. So it looks something like that. All right, so sketch the curve represented by the parametric equations, then eliminate the parameter. In other words, find an equation with only x and y to write the rectangular equation. So if you're sketching the curve, then you would do a t-table. I'll let you go ahead and use your calculator to sketch. So we're going to put in 2 times t plus 1 in parentheses. Oops, my parentheses didn't show up.
I don't know how you keep getting that. I have tried the windows and the.
How I keep getting what?
How you keep getting the graph. Like,
I'm just getting it.
Yeah.
And I'm wondering if
it's not showing up at all. It's like.
Yeah, mine too.
All right, so let's go through everything. So hit your window. So on this one, let's say I want from negative 10 to 10. We'll do that. And then your t-step should be like 0.1 or 0.13. I mean, maybe the best thing for us to do is just do zoom standard. So hit zoom standard.
Z standard?
Yeah, so hit the zoom button and then do Z6, just like the normal. So now we're all the same. Now adjust from there. So like I'm going to do negative 10 to 10 for my Tmin and Tmax. So I use negative values and positive values.
T-step should be like -1.
Oh wow.
T-step should be positive 0.13. All right, and I hit graph. All right, now do you see like a line?
Yeah.
Okay, so what we're saying is if we can eliminate the parameter, if we can like solve for t and plug it into the other one, we should get the equation of a line. Okay, it's going to be equivalent to something that you could have graphed in Algebra 1, basically. So when you do this, where does t look the easiest to solve for? Like the y one, right? Does that make sense, the y equation? So if I subtract my 3 over and then divide by a -1, I get 3 minus y is equal to t, or negative y plus 3. So once you do that, you go back to your other equation and you replace your t. Okay, so your t is going to be replaced by 3 minus y plus 1, like that. So we get x equals 6 minus 2y plus 2. So x equals 8 minus 2y, and you could solve for y, but you'd have an equation of a line, right? So you'd have x minus 8 over negative 2 equals y. So y equals -1/2 x plus 4, just like Algebra 1 when you tried to solve for y. Get it in the form y equals mx plus b. Okay, does that look like the line that we had? So let's check. Does it look like it has a y-intercept of 4? Yeah. Does it look like it has a slope of -1/2? Down 1, right 2, down 1, right 2? Yes. Okay, so we've eliminated the parameter correctly. Okay, so I understand, like, a lot of people are like, well, why do we do a parametric equation then? Why don't we just keep it in this way? Because then you aren't going to be able to graph anything that, like those spirals and the flowers and so on. But it's also very useful for these the parametric equations that I was showing you. Like, as something's going in the air, having an x component and a y component. Guys, pay attention. All right, so this next one. So if we graph this. So you're going to go in here and you're going to do x equals. So we're going to have natural log of 2t. And then we're going to have 2t squared. All right, so we're going to hit graph. All right, so it looks like an exponential curve, right? Like, remember y equals a to the x, something like that. Has kind of a horizontal asymptote. So let's try to eliminate the parameter. So we can solve for t here, but it would involve like a plus or minus. Let's try to solve for t over here. Do you guys remember how to get rid of a natural log?
Like e to the x?
Yeah. So you're going to do e to the x equals 2t. Exactly.
Good job, Tyler.
Right? Because that's natural log is log base e. So if you have log base e of 2t equals x, when we switch forms, we do e to the x equals that part. That's all we did. All right, so that means e to the x over 2 is equal to t. So we take that, now that we've solved for t, and we put it into the other equation. It's like substitution elimination, kind of. So we're going to do y equals 2 e to the x over 2 squared. So we end up getting 2 times, what do you think this is going to be? Is it going to be e to the x squared, e to the 2x? What am I going to have? It's going to be e to the 2x. Remember, multiply your powers over 4. So your final answer then would be y equals e to the 2x all over 2. That's our answer. Okay, that would be the equivalent equation in x and y without a parameter. Do you see how this works? All right, so try this one. So what's the easiest thing to solve for? Like which equation? X or y? Y. So y is just going to be 5t, so that means t is going to be y over 5, right? So I take that and I plug into the other one. So I'm going to have x equals y over 5 squared minus 1. So I'm going to have y squared over 25 minus 1 is equal to x. Do you guys know what kind of shape that should be? Think back to algebra 2. It's a parabola. Is it up and down, right and left? What is it?
Right.
Yeah, it's a sideways parabola, right? So if you check that one, oops, I got rid of my little graphing calculator. This one's, oh, there we go. All right, so if you check it, you will get a parabola on its side. So if you do y equals, and you put it in, are you guys going to be pros at putting this in? X squared, or t squared minus 1. And then we have 5t. So we hit graph. And we have a parabola on the side. Now if you needed to zoom out, you can. You can always do your zoom 6. But the problem with zoom 6 is it's really used mostly for like polar type equations, 0 to 2 pi. That's always your T min and T max. I would make sure that you include negatives as well. So I usually go from -10 to 10. And then if I don't see all of it, then I do more. Okay. All right, so it says use every multiple of pi over 4 on the interval 0 to 2 pi to make a guess at the rectangular equation for x equals cosine of t and y equals sine of t. Okay, the table has been filled in for you. So basically it's saying plot all of these points right here. Okay, so if I have 1, 0, we know it's here. If I have 0.707, 0.707, it's really root 2 over 2, root 2 over 2. 0, 1, what do you think is going to happen? Negative and positive 0.707. Negative 1, 0. What am I graphing? It's my favorite. Yeah, it's the unit circle. You guys see it? So what we would end up getting is the unit circle. Okay, so what do we think the equation, a rectangular equation with x's and y's? How do we do the equation of a circle? Well, usually, yeah, x minus h squared plus y minus k squared equals r squared, right? Oops, r squared. So in this case, we have x squared plus y squared equals 1, and that's our answer. So why does that work? Here's what's happening. X is cosine. If I take cosine squared and I add it to sine squared, what do I always get? 1. That was one of our Pythagorean identities, right? That's why it works. Okay, so this next one, it's going to be very, very similar. Okay, but we're only going from 0 to pi, and you can graph it on your calculator if you need to. But basically what you're going to look at is what happens when I do an x squared plus y squared. So if you see sines and cosines, always do that. So we're going to have 2 cosine t squared plus 2 sine of t squared, which is going to be 4 cosine squared plus 4 sine squared. What does that all equal? That equals 4 times cosine squared plus sine squared, right? Which ends up just being 4. Do you guys see? So this equation then is the circle x squared plus y squared equals 4. Okay. Now here's the weird thing. So let's graph it because we have a domain thing too. And then tell me what you think is happening. All right. So when you graph it, we have 2 cosine of t, and we have 2 sine of t. So when we hit graph, we have a circle. Its radius is 2. All right, but if I want my window to go from 0 to pi, it's not going to graph that whole circle. Okay, it's only graphing the top. Do you guys kind of understand why it would do that? It's doing like a t-table, plugging in t equals 0, t equals all these different values like pi over 4, pi over 2, until we get to pi, and then it stops. Right? It's only doing the top part of the circle because of that. Does that make sense? So what do you guys think the second one's doing if I go from pi to 2 pi? So this was only doing the top part. Top part. So what do you think the next one is? It's the x squared plus y squared. What do you think the r squared is going to be? There's like a pattern. Are you guys seeing the pattern? What's going to be the radius of this? Yeah, the radius is 3, so 3 squared is going to be 9. Do you guys see where we're getting this? It's coming from the number in front of cosine and sine because it's like what the whole thing would equal. It would follow the same pattern. All right, and then when you graph it though, it's not giving you exactly this whole circle. It's giving us only the bottom half. It's a semicircle. You guys see that? So you could graph that on your calculator and you would have that. All right, so one last thing to talk about. All right, so the parametric equation for a line through 2 points. Your book loves these problems. I don't know why. So if you want to find a parametric equation for a line through 2 points, A and B, there are 2 steps that you're going to need to follow. Okay, so it's really easy. Step 1, so it says find A, like the vector AB, as we did in the previous section. So remember, if you have 2 points and you want to get their vector, what we do is we just take the x2 minus the x1. So -4 minus a -1. Oops, I didn't do my pointy thing. So I do -4 minus a -1, and then I'm going to do 1 minus a 7. Do you guys remember that? So we end up getting -3, comma, -6. Okay, that's going to be like our starting point. Okay. Well, not our starting point. Then we're going to pick either one as the starting point. So let me draw it out. So we have -1, comma, 7. 1, 2, 3, 4, 5, 6, 7. And we have -4, 1, 2, 3, 4, comma, 1. And we're trying to find the equation of this line. Oops, missed it. In parametric form. Wasn't even close, was I? All right. So what we're saying is we're going in the direction of -3, comma, -6.
It's 1, 7, what did you have next time?
What did I do? -1, comma, 7. It's right here. And then -4, comma, 1 is here.
What is it? Just 1.
It's -1. Right? A is at -1, 7. Did I do that right? Am I crazy? Is that right? A and B? Those are my 2 points. All right, so AB is going to be in the direction -3, 6, -6. Like that. So it's going to be like that. Do you guys see how it's like pointing in the same direction as the line we already drew? Okay, that's what we're saying. We're going to go along that direction. Okay, so we're going to pick any point as the starting point. So pick either point. So let's say we pick A. We're going to write it as a vector, -1, 7. And we're going to add it to t times whatever we just found for AB, -3, -6. All right, and then we just simplify. So we're adding our components. So we get -1 minus 3t, comma, 7 minus 6t, like that. Okay, and it basically creates what we call, like it's a parametric equation. It's the x values are in the form -1 minus 3t, and the y values are in the form 7 minus 6t. So if you did like a t-table and you plug it in t equals 0, okay, you would get the point -1, 7. Do we have that point on our line? Yes. If I plug in t equals 1, I would get the point -4, 1. Well, -4, 1's right here, right? So you get all of those different points on the line. So that's how you would write a parametric equation. So if I have AB here, AB is going to be x1 minus, or x2 minus x1, so -4 minus a -5, and then we're going to have 8 minus a 2, like that. So I get 1, 6, like that. And then I'm going to add that to any of the, well, I'm going to multiply by t and add it to any point. So if I take my negative 5, 2, and then I do plus t times 1 comma 6, I get my parametric equation. So I'm going to combine. I have negative 5 plus 1t, and then I have 2 plus 6t. Combine just like you would think you do. Distribute the t in, combine your x's and y's. So we get x equals negative 5 plus t, and we get y equals 2 plus 6t, like that. Okay, and that's our answer. All right, so I realized this section was a little bit longer than what I wanted it to be. So the different things that I would put on a test for this section. I definitely want you to know how to do the component form for velocity. Okay, and I can see myself putting something like this first one on there. Okay, I won't put the second one on there. I didn't think about it. It's a lot harder than what I wanted it to be. But the first one, if you guys graph, like you can graph this equation. Like you can graph this in for your, whoops, I'm trying to circle it, but it's not circling. You can graph this for your parametric equation and this for your parametric equation, and you can kind of work from the graph, like use your graphing calculator to help you. But I don't think it's too bad to do by hand either. Like finding when it reaches its maximum height or anything, I don't think that was very bad. So yeah, so like example 1, maybe put a star next to that. But example 2, if you just want to cross it out, that's fine. I also want you to know how to graph things on your calculator using different t-mins and t-maxes. Are you able to do that on your calculator? Can you eliminate a parameter? Probably not for the natural log type things, but can you do it for this type of stuff? Yeah, you can do that. I totally trust that you can handle that. And then kind of know the formulas. If you have like sines and cosines, that's going to be a circle, and decide if you have the whole circle, if you have part of the circle, and then know how to find the parametric equation through a given point, okay? So don't worry about the initial velocity one. That was just mean. I should have thought that one through.
Can you go back to the last page?
Yeah. Oops.